All right. Let me get your attention, please. Thank you. So it's been a week since we had our last lecture, okay? And on Wednesday you guys took the midterm exam, and I'm going to get together with the TAs and readers to grade them this afternoon. So we're hoping to finish and get your grades posted. I'd say by the end of the day. That's the goal. There could be some snags that might slow us down, but I'll keep you posted. Okay, let me just kind of review what we talked about last Friday, and then we'll continue on. Okay. And so far what we've covered is we've covered the Metropolis and Metropolis Hastings algorithm. And we said this is a way for us to sample values from a distribution. And in particular, it's useful for us in the Bayesian context because in the Metropolis algorithm, the fact that whether you decide to move or not is based on the ratio between the probability of a proposed location versus the probability of your current location. And when you take that ratio, if there's a normalizing constant that's difficult to calculate, that normalizing constant is canceled out. And that makes the process a lot easier and doesn't actually require us to have the actual PDF. And we can just have something that's proportional to the PDF. All right, does that sound familiar? Okay, so we can work with something that's just proportional to the PDF and not the actual PDF. And then, and so on Friday, I introduced this problem saying there is a cipher that we want to decode, and we want to be able to create a posterior distribution, which is going to be equal to the likelihood times the prior divided by the marginal probability. And we said, well, the marginal probability is a constant, so we can ignore it, okay? And also, the prior distribution will be uniform, so that will also be a constant, okay? And therefore, we can also ignore that. And so therefore, our posterior distribution is just going to be proportional to our likelihood. And now, what we need is we need to create a model to measure the likelihood of our data based on some hidden parameter. And in our case, the hidden parameter is the secret decoder key that maps each letter onto another set of letters. Okay, that's what we want to do. And so we said, well, what we're going to do is one way to measure the likelihood is to say, if this were the decoder key, then the original message is this word. Okay, are these words, or is this string of characters? And if in that string of characters we have real actual words, we want to say, oh, this decoder key has a higher likelihood. Okay, whereas if after we say if this is the decoder key and the original message was this, if the original message was completely gibberish, we want to say, well, that's less likelihood, right? Less likely, okay? So if this was the decoder key, if one of the decoder keys was this, and it says, well, the original message, in order to produce the message we intercepted, the original message had to be this, we would say, well, this decoder key must not be any good, okay? Whereas if we had a decoder key that looked like this, and it said, we intercepted this message, which means the original message was this, we'd say, okay, that seems pretty likely, okay? There's a limitation though, okay? And the limitation is that because we're looking for real words, if we have two possible decoder keys and they both translate to non-English words, if we used real words as our only measure of likelihood, both of these phrases would get the same likelihood score of very bad, okay? They would say none of these are real English words in the second row, none of these are real English words in the first row. Both of them are going to get a very low likelihood score, okay? However, as far as decoding goes, okay, the decoder key that says this was the original message seems a lot better than the decoder key that says this top message was the original message, right? Because even though they are both nonsense words and they are clearly the wrong decoder key, the one that produces the second line seems more correct, or it seems like these resemble at least words versus the one that produces the first line. Does that make sense? Okay, and so we also want to include the ability to compare these two and say this one is not correct, but it's less bad than this one, okay? And so in order to do that, we are going to take a look at basically two-letter combinations in the English language, okay? So this is where we're going to pick up today. All right, so we're still in our deciphering problem. Okay, and so we have two wrong decoder keys, and they both produce nonsense. Okay, but we want to say that the second line is, I would say, less bad than the first line, even though it also produces nonsense. Okay, because the second one looks, less bad. Okay, so to do this, our model will also include, a way to measure likelihood, measure probability or likelihood based on two-letter combos. Okay? So we want to say, in English, the letter combo NG, common. Okay? TA, T followed by A, also common. Okay? TH, common. All right, but then others, NQ, all right, uncommon. All right, X followed by J, very uncommon. And so for this, we're going to have basically A, B, C down to X, Y, Z, and space. And then A, B, C to X, Y, Z, space, a 27 by 27 matrix. Representing how common each letter combo is. Okay, so we would expect the T and the H, this one to be, I don't know, this one will be large, okay? Whereas Z followed by Z, you know, this will be pretty small. I mean, buzz, fizz, how many words have double Z? Dazzle, razzle. Okay, all right, there's a few words, but not a ton, all right? There's lots of words with TH. There's lots of words with NG. There's lots of words with, I don't know, IE, okay? Not a ton of words with ZZ, not a ton of words with XJ, or, I don't know, maybe that was funny, okay. All right, and so, so basically our likelihood, okay, we're gonna say the likelihood of a decoder key, theta, okay, given our fixed intercepted message. Is going to be equal to two parts, okay? There's going to be two parts that kind of find this decoder key. And it's going to be, one part will be the actual words, and then the other part will be the two-letter probabilities, okay? So it'll be probabilities of actual words versus, you know, non-words, plus the probability of basically the two-letter combos. And we'll include some kind of, and I should say this is proportional too, okay? It's going to be proportional. No, the likelihood will be this, and the posterior is proportional to this. And we're going to have some kind of mixing weight parameter, okay? Because we basically are, the way we're measuring likelihood consists of these two components, and which one do we give priority to? Do we say the two-letter combos is more important, or do we say that looking for actual words is more important? We can control that by using a weight parameter, okay? If we want to say the two-letter combos are more important, you know, we make the weight parameter bigger than 1. If we want to say the actual words are more important, you make the weight parameter over here smaller than 1, okay? So we have kind of these two competing, maybe they work together, but we have these two different priorities for measuring how likely our data is given, you know, for some fixed, for some decoder key, okay? All right, and so kind of the code here is if we're going to deal with log probabilities, okay? So this would be, these would be products, but then if we deal with log probabilities, so the log likelihood, this will become the sum of the log probability of each word or non-word that appears okay, and I'm sorry, here I should have a multiplication. Sorry, let me, multiplication sign with a lambda up there, and this becomes plus lambda times the sum of the log probability of each two-letter combo. Okay. All right. Is this okay? Kind of this idea of, it's just a simple way to decide whether you know, one original message is more or less likely than another original message. Okay. And what we're going to do is, you know, we say, here's my decoder key, right? So here's my, okay, I have my intercepted message. And then we say, if theta is the decoder, here's the, quote, original message. Then original message is this. Okay, so here's our intercepted message. If theta is the decoder, then this is our original message. And we need a way to evaluate which original message is more likely than another, okay? Okay, and then by doing that, we can, we know that our posterior distribution of theta is proportional to our likelihood function, and therefore we can use this to sample different values of the decoder key, different possible decoder keys, and even if we start at a terrible location, the way the Metropolis algorithm works, and I hope you saw this in your homework, is that you can start off at a terrible location, but the Metropolis algorithm will end up getting you towards a location of high probability, okay? So we can start with a terrible decoder key, theta, okay? And the Metropolis algorithm favors moving towards areas of higher probability. Okay. All right, so I'm going to go ahead and I have all of this coded up here, and I'm going to just, it's a big chunk of code, but I think I can talk through it and make sense of it here. Okay, so here's my cipher code, all right? Okay, so I have just I have a big tome of text. I have War and Peace, the entire novel. Okay, it's 3 megabytes of text. It's I don't know how many chapters this is. It's in Roman numerals. What's this? 28 in book 1, 21 in book 2, and 29 in book 3. How many books are there? 6, 7, 8, 9. Okay. Just the table of contents has 826 characters in it, 826 lines. This is going to make it sure seem like II is a high two-letter probability, two-letter combo, but whatever, we'll suffer the consequences of that. Okay, and here it starts off with, well, Prince, so Genoa and Lucca are now just family estates of the Bonapartes. Okay, so I don't know. I haven't read this. Has anybody read War and Peace? Okay. Yeah, well, we're stats majors after all, so. Okay, so anyway, well, we're going to read that in. We're going to bring this in here. I'm going to set up a 27 by 27 matrix. And basically, this code basically just says, for each line in War and Peace, look at one character and look at the next character. And so if you see an A followed by a P, then add a 1 in the A followed by P location in the matrix, okay? And then move the P over, and then go to the next letter, and I don't know, if you see a P followed by a P, then add a 1 in the PP location. And then you see a P followed by an L, and then you add a 1 to the PL location, right? And so we do that, and we go through the entire thing of War and Peace, and it's like many, many, many lines. Okay, so this will take a little while, all right? And I think I've saved all of this somewhere, but so we'll let this in, and it's just going through every single line of text, and it's looking at every 2 letters combos, and wherever it sees, one letter followed by another letter, it adds a tally, or it adds 1 to somewhere in that matrix, okay? And then so I guess it's going to run, and what we're going to do is the entire matrix we might have gone through in all of War and Peace, and maybe we never found an instance where the letter Q was followed by the letter J, okay? That's very possible, because I don't know very many words where Q is followed by J. But having a 0 in the matrix can cause a problem, because it is possible that somebody wanted to send a message where Q was followed by J. And so we don't want to say the probability of that is 0. So we're just going to go ahead and add 1 to every single one of these values, okay? And then we're going to just divide by the entire kind of the sum of the matrix. And so that, so anyway, we get this, and I'm going to just go ahead and plot this out so you guys can see this 27 by 27 matrix. Cannot find function melt. Okay, there we go. And so here is the 27 by 27 matrix, but represented with colors. And we can see H followed by E is very common. T followed by H is very common because the word the is very common, okay? And we can see also I followed by N, very common. And we can also see rows like where J, this entire row for J is pretty blank because J just doesn't appear very often, okay? And and then the letter Q has almost no, Q is almost never followed by any of these letters, and we have just an ever so light patch of gray for Q followed by U, okay? And everything else is blank, okay? Z doesn't appear very often and stuff, okay? We see, and you can also kind of identify the rows with vowels because they're just darker rows in general, right? A, E, I, O, R, S, and T. These rows appear darker because they're more common, stuff like that, okay? So anyway, this is our 27 by 27 matrix representing 2-letter probabilities. Okay, over here, I'm just creating some functions that will allow us to encode and decode words. Okay, so this represents just some random decoder key, and it says basically that the letter A goes to the letter S, and the letter B goes to the letter M, the letter C goes to the letter J here, okay, if you guys can see that. Yeah. Shrink this, move this up a little bit higher. Okay, and so here is the word hello got mapped to UMZZT, all right? And we can see, okay, well, L got mapped to Z, right? Because it's the last letter here, and that's why, that's what happened, okay? All right, and then, and DMAP just undoes this, okay? And if we decode, if I say decode, with the DMAP using UMZZT, it says hello and I don't know, some other message, right? So you can decode and you can encode and decode with using our map and the demapping things. Okay. So anyway, for the log probabilities of our two-letter transitions, basically it just says, all right, take the string that we've decoded and then just look at every two-letter combo that you see in your decoded string and then go to that 27 by 27 matrix and look up each thing. So in your decoded string, you find U followed by K. Then you go to the matrix and you say, what's the probability of U followed by K? Oh, it's 0.002, all right? Then, and then in the next string is, K followed by R. What's the probability of K followed by R? You go to the table, 27 by 27 matrix, and you say K followed by R has this probability. And you look that up for everything in your decoded string, and you get a score for the decoded word or the decoded phrase based on the two-letter probabilities. Okay? Does that kind of make sense? All right. And then over here, we're going to incorporate the ability to measure how likely the words are. Okay? And we have this file called the Lexical Database. And I'm actually not sure where this lexical database came from. Okay, this guy Drew Conway worked on it. There's a severe deficiency with the lexical database, and it could probably be improved. But the lexical database right now, it's basically got a list of all the words in the English language, and it has a probability associated with it. But it doesn't have any plurals, okay? So it'll say the word apple is common, but apples, that's not a real word, okay? So that's a problem. It's a problem, okay? But I mean, it'll still help us, okay? So we just don't want to say anything like this. But here is, if I do like the 1 gram probability and I give it the word, I don't know, apple, and I say use the lexical database, okay, it says the probability of that word is that, whereas the probability of word this thing, we just assign it to the value 1 times 10 to the negative 10. So it says if it encounters this word apple, it says that happens with the probability of basically 1 to the 10 to the minus 5. If we encounter the word the, that happens with about 5% probability. I think that's going to be like one of the highest. So about 1 in 20 words in English is the, apparently, okay? Other words like, I don't know, is quite common and things like that. But then unfortunately, and then if for words that don't exist, okay, we just give it a very small probability. Not 0, okay, because 0 would cause problems, but we just give it something on the order of to the minus 10, right? So, I don't know, what's a... Is this a real word? Okay, that's not a real word, according to the lexical database. Aardvark? Okay, so that's not to the minus 10, it's 1,000 times more likely than that. But I think it's missing plurals. Yeah. So it recognizes aardvark, but it doesn't recognize aardvark. So that's a problem. But I don't feel like going through and trying to figure out the probability of plurals and stuff. So, but we could probably fix it up by doing word stems. Okay. And then so anyway, log probability of text. Basically, that takes a text string. And then it splits it up, right? So we've got apples and aardvark, and it says, okay, your score here is going to be this. Whereas if I put in, apple and aardvark is this, but apple jika 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 and it's two nonsense. Oh wait, what is going on here? Both of these are giving me maybe maybe I need to split this up. into, I think, let me see. This is, I have to think of, oh, I didn't specify the lexical database, that's why. That's why. Okay, so that's what we want. And there we go. And then when we give it real words, it says it gives us better scores here. Okay, so I just have to specify this, and then if we said the is, this gives us a higher score type of thing. Okay, so it takes in kind of the translated text and it looks for these real words, and if it finds a real word, it gives it a better score. Whereas if it's just nonsense words, it says boo, bad score. Okay. And then meanwhile, the other function that we created, log prob, this was based on the two-letter transition probabilities. Okay. So words like the, I think requires the decoded thing. Okay, so I don't feel like messing with it, but basically it says that. Okay. There's a question. Yes.
Like in the last one you just did, like, is it looking for like what is as a string or like as two separate?
It sees them. It splits it up by the spaces, and it sees them as two elements, and it says, "Do I find the word the the in my database?" And we say yes, and it's a very common word. Okay, so it gets a high score or a low negative score, because in log probabilities everything's negative. And then is that in my database? Yes, it is. It's very common. It gets a small negative score. So the is gets a score of only negative 7.8, whereas apple aardvark, those are both real words, and they get a score of negative 24. And then, non-real word here and real word aardvark gets a score of negative 37, and then two fake, this should just be spaced with a space. Two fake words will get a score of negative 46. So and then log prob with depending on, let me just do. All right. The other function, which requires me to have a mapping and a demapping, tells us basically the probability of some kind of translated, basically based on the two-letter combinations. Okay, so here we are going to say this is going to be our string that we're going to encode. All right, so we've intercepted a message. The original message is from Hamlet, all right, and it says enter ham, and Hamlet says to be or not to be. That is the question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against a sea of troubles and by opposing end, right? So this is, right, Hamlet is not sure if he should kill his uncle not Scar, well, anyway, Lion King and Hamlet are the same, basically, because his uncle betrayed his father, and right, his father visits him as a ghost and says, I don't remember what he says. Remember who you are, Simba, and you got to go and fight. But anyway, so Hamlet, yeah, okay. But in Lion King, they live happily ever after, and spoiler alert, Hamlet, they die. But anyway, so this is the original thing. Hamlet's deciding whether or not to fight his uncle. and he can't make up his mind, and it kills him. But anyway, we just take a random mapping, okay? And then after we've encoded it, this is the message, right? And so this message is being passed, right? I don't know, in prison, they just want to practice their lines of Hamlet. And the guards think they're up to no good, and they intercept this message, and they say, we've got to figure out what the prisoners are sending to each other. And so we want to translate this, right? But they have no idea, so we're just going to start with a terrible, just a random guess, okay? We're going to just start off with a random guess, and when I use my current random guess mapping, this is the message that we've encountered, and when I try to say, all right, here's a random decoder key that I've made up, and I use that, it says, okay, well, when we decode it, this is what we get, all right? And we get, well, this is no good, all right? This doesn't help me understand. You just map the letters to another set of nonsense letters, okay? But now we have a way to measure how good or bad this original message is, okay? So we calculate the current likelihood and the log likelihood of the text, and we say, okay, well, what is the score that this gets? Okay, this score gets a score of negative 1700, okay, which is probably pretty bad. And so what we're going to do is we're going to just start our Metropolis algorithm, okay? And the Metropolis algorithm, the way it's going to work, oh, I never talked about the proposal function, but we have a current mapping which says these 26 letters go to these 26 letters, okay? And we're going to propose a new mapping, all right? And in order to kind of control, just so it's not like, here's 26 random letters, and then let's just pick another entirely random 26 random letters, because that would be independent sampling, right? If we just said, here's one random mapping, let's just try another random mapping and see if it's any better. All of those random mappings would be independent of each other, okay? But the Metropolis algorithm says independent is not helping us learn. Let's take the one we have and just take a small step one way or another. And in this case, for letter mappings, we're going to just say, okay, here are my these 26 letters are being mapped this way. Let's just pick two random letters and swap them. Okay, we're going to take two random letters and swap them. So basically, the resulting mapping that we did get after swapping the letters will be almost exactly the same, except, A's are now K's and K's are now A's or whatever, we've just swapped two letters, okay? But that allows us to compare one versus another. Rather than having two completely different ones and saying, I have no idea, we can just make incremental changes and then compare them and say, oh, this one's better. Or, no, the original one was better, okay? So for our proposal, okay, so for the Metropolis algorithm, our proposal is take the current mapping of 26 letters and just switch two of the letters. Okay? And so that's what we've written in the code, all right? So the proposal is just going to say from 1 through 26 sample two numbers, okay? And then we switch these things, okay? The proposal mapping, 1 gets moved to position 2 and 2 gets moved to position 1, okay? And then we apply that new proposed mapping to decode our text, and then we calculate the log probability of the decoded text now. And we say, all right, here's what it originally was. It was bad. After we swapped two letters, was it any better? Okay. And so when we do this, it starts running. Okay. And so here it starts off with just terrible nonsense. Okay. But it's just doing this, and it's just switching two letters at a time. And already if you remember what it originally started off, it started off as completely terrible, but now we're getting things that it's still nonsense, but at least these things kind of look a little bit like they could be words, right? And oh my gosh, we've got, something. For a second I saw B in there, right? To be, okay, we got to P on, and on rot to P, okay? And we were like, okay, Ayrton Howlett, okay? So not enter Hamlet, but we're kind of getting there. And all it's doing is it's saying, what if I swapped these two letters? Is this any better? Okay, and we have a way to measure what's better, right? We say, if it looks like real words, that's better. If it gives us two-letter combos that are more common, that's better, okay? And and we got enter hadlet, had to see or not to see. That is the question. Keder tis knockler in the Ming to suffer the slins. But we're starting to get the, and look at this. We got it. Enter Hamlet, ham to be or not to be. That is, okay, we haven't gotten question, all right? Chether tis nobler in the Ming. But we are, the point is we've started off with a completely random set of 26 letters saying these 26 letters are going to go to these random 26 letters. And it was obviously terrible. But then we just swap two letters at a time, and we say, and we had a way to evaluate whether something was better or not. And by using that, and the Metropolis algorithm, which says if it's better, definitely move, and if it's worse, maybe we'll go, okay? And so it's not a strictly everything has to get better every single time. It'll just say, okay, if it's worse, maybe we'll go. And now we're at a point where, we can, I would say we've successfully translated this, right? And there you go, all right? And I would, this is, I would have to say this is technically, the outputs you're seeing are not the actual samples, because in the Metropolis algorithm, when you sample and you reject, you end up you use that value as part of your sample. And here it only updated it when it made a change, okay? So it's what we're seeing here, and these are just the results of the new decoder key. But at this point, we've got it, right? Enter Hamlet, to be or not to be, that is the question, whether 'tis nobler in the mind, to suffer the slings and arrows of outrageous fortune, or to, okay, it didn't get take, it has tave arms against a sea of troubles, and by opposing end, but I would say pretty successful, and if the prison guards got this, they would say, oh, okay, they just want to work on their Shakespeare, and that would be a good thing, right? But kind of just scrolling back and looking at where we started, if we look at this, it was total gibberish here, right? This didn't look like anything good, and then and we just swapped letters at a time, 2 letters each, and we just said, is this better? And we had a way to evaluate it, and eventually we got to a point where we were able to do that, okay? So, and if you think about it, okay, the true distribution, if we think about all the possible values of our decoder, we said there were 26 factorial of them, right? And that's just way too many to try to evaluate. But, and we don't even know what the actual PDF looks like. But because we can say it's going to be proportional to our likelihood, we didn't have to bother figuring out the actual PDF. We just say it's proportional to this likelihood. And then the Metropolis algorithm says you don't have to do all 26 factorial. Just start somewhere, and the Metropolis algorithm takes incremental steps that favor getting better. And basically after 177 changes, okay, so we probably had to sample a lot more, but 177 changes are accepted things. We're at a point where I would say we've we've successfully decoded the cipher. So anyway, I thought this was kind of a neat little thing of how the Metropolis algorithm works. I'll post the code up and you can kind of read through it. It's a lot, but generally the pieces of the Metropolis algorithm are all there, okay? And we didn't do anything more complicated than that. Okay, with that, have a good weekend, and we'll see you guys on Monday.